our next speaker is Volker Huber. So he's going to give us an introduction to small angle neutron scattering. So we are right in time, Volker.
Sure, sounds good. Okay, so my name is Volker Urban. Well, we did the introductions earlier a little bit. So I will be giving a kind of a very basic level introduction in small angle neutron scattering. We have a diverse audience today. I know some of you have already done small angle scattering, so some of this may be familiar to you. So then relax and take it as a refresher. But I'm assuming that we have people in the audience who do not know anything about scattering or maybe even diffraction. And so I'll start there. There's a lot that one could say about small angle neutron scattering. This means that much more than that fits into this lecture, so I'll have to leave a lot of it out. But I hope I'll get across some core concepts that will help you as you go forward. Can you hear me okay? Microphone check? Good.
Yes.
Okay. Thank you. And I hope to go through this in less than 45 minutes, so we have some time for questions at the end. Okay. So I start with this picture sometimes, this lecture. What you see here is an effect of scattering. It's light scattering, in this case, sunlight scattering off of mist, right? That means very small water particles. So we're all familiar with scattering in some form or fashion. There's also one of the key concepts here that we can already explain at this example, and that is you see these sun rays because the light scatters off of the little droplets. You do not see the individual droplets, but you see the collective effect of the light scattering, and that applies also for small angle X-ray scattering and neutron scattering. So you'll find some intensity distribution of scattered rays without seeing the individual particles. So it's not like microscopy in that sense. So my lecture is structured like this. I will be talking about basic concepts first. I have a fairly long segment on the size and shape of scattering particles, so what's often understood as the form factor. I use this as kind of a pedestrian approach, walking you through what happens when you change the shape and how this is reflected in scattering curves. That kind of lecture you probably don't find that often. I kind of find it intuitive, so I'd like to share my intuitive approach with you. Hopefully you find it helpful. And then I'm going to go a little bit broader into interacting particles, but that will be much more briefly. And then I'm going to go back to contrast at some point. Hugh already mentioned contrast for neutrons in his overview. I'll talk a little bit more at the beginning about it just for the very necessary, and then I'm going to go a bit more into detail at the end. And then I have some summary, and there are also references listed at the end of my slides. So I think all of us understand microscopy. It's pretty straightforward. You look at images that are at pictures, at images that are magnified. Scattering is not like that, but it does operate in a similar range. So if you think of electron microscopy and scattering, both operate in the nanometers to micrometers range. Both have contrast labeling options. So to see anything, you need contrast. If everything looks the same, then even if it's there, you still don't see it. So that's one way to put that probably. The small angle scattering, and sometimes I just say SAS, because much of what I'm saying today applies to small angle X-ray scattering just as well as to small angle neutron scattering. So contrary to what you normally need to do in like electron microscopy, you do not need to do a special sample preparation. So you can use your samples in many ways in the way you find them, even in nature-like environments and things like that. And you have a wide range of sample environments control. It's also a non-invasive technique, so you're not actually needing to cut up your sample and prepare it in a certain way. You can actually use it for something else afterwards. With X-rays, you can sometimes have radiation damage. With the low energy neutrons that we use, we do not get radiation damage either. You can sometimes get some activation, and you may have to wait for your samples to decay. So if you have, for example, sodium in your system and things like that, but you're not destroying your sample. And you can do it in situ, like I said, so you can have it in different environments, and you can change parameters of your environment. You can do a pH titration, or you can cook the sample, so you can apply pressure, and you can see how it changes over time with the scattering techniques. Now, the fundamental difference between microscopy and scattering, very fundamental, is that in microscopy you see a real space image with a certain resolution. In the scattering pattern, you do not see images. You see the scattering intensity distribution, and you average that signal over a volume that you probe. So that's very different. But the two techniques are often complementary. So that means we often use both of them to get at different parts of information. And one example I have on my next slide, that's just one example from actually some long time ago. We measured this. These were beta amyloid structures, and you may relate to, them to being related to Alzheimer's disease. The point I wanted to make here is that with electron microscopy, we were able to find these kind of resolution images where you can see the twist. And then you can use scattering where you don't see that kind of image, but you can measure some details like how thick is this exactly, or what is the mass per unit length? How many of these sheets do you put together? You can actually kind of measure the weight per length, something like this from your scattering experiment that you do not get with that kind of resolution or detail in the microscopy. So that's one way how this can be complementary. There are other examples. Okay, so this is kind of summarizing the fundamental difference. Microscopy, you put some kind of beam on your sample, either a light, intensity light to illuminate it, or electron beam if you do electron microscopy, and then things bounce off of the atoms or the features in your sample, and then what you need is focusing optics to take that intensity that bounces off the sample and put it into an image. And an image can be the same size, or it can be magnified, and you have microscopy when you magnify it. Now, in the scattering techniques, you also put a beam on the sample. They also bounce off, but you don't have any focusing optics, and you don't get an image. You get instead the scattering intensity distribution. And usually we put a detector at a certain distance, and then you measure what intensity do you get at which angles. And there is this what we call theta, that scattering angle, that is the angle relative to the incoming beam axis. And then there's also what we sometimes call an azimuthal angle, so the angle in this plane. So that kind of defines where you are relative to the incoming beam and defines the scattering pattern. Now, as I have shown in this example, this is actually a real scattering intensity pattern that I measured very long time ago on stretched rubber samples. You can see this one's anisotropic, so it has a certain shape. It's not just circular. So that can happen. You can have two-dimensional data, and there's a lot of information in those if you have preferential orientations in your sample. I'm not going to go into this into any detail at all today. Venki Pingali in his presentation on the hierarchical structures will touch on this a little bit more. In many cases of small angle scattering, we have isotropic patterns where all of this is circular. That's similar if you're familiar with powder diffraction, with the rings in the powder diffraction pattern. They're circular, and they're isotropic, and all of the information is just in this theta angle, so in the angle away from the beam. And that's what I will be focusing on today. So we usually call this then isotropic samples. And a good example is solution scattering. So if you have anything in dilute solution, there is usually no preferential orientation of scattering objects, and you'll find a circular pattern. Now, if you have a circular pattern, then you can average that around these rings, and then you get what we sometimes call one-dimensional data. We call this also reduced data, where you then plot the scattering intensity away from that beam with increasing angle, and you can see how the intensity drops off. Now the skew, I'll get to this in just a second, basically is related to the scattering angle here. So as you go from high intensity in the center to lower intensity outward, typically, not always, but typically, you get a drop off like this. And so many scattering curves look like somewhat similar to this. And then, yeah, so that's called the reduced data. Now, the scattering vector here is not just the angle, as it also includes information on the wavelengths, and I'll get to this next. So the scattering vector is central quantity. Sometimes it's also called momentum transfer, and you'll find different symbols in the literature. We often use Q, a small q, or a capital Q. but other authors have also in the past used H, K, and S, and it also varies a little bit on whether you're doing X-ray scattering or neutron scattering. There's just different preferences, and they have developed historically at different times. So don't get confused by that. But I'll be using Q today, and we are in this workshop actually we'll be using Q, but we will be using capitals and small q's. They mean the same thing in our context today. If you're familiar with Bragg's law in diffraction, then this is one way how you can get into the meaning of what this Q is all about. So to recall, Bragg diffraction is described as reflection by lattice planes. That is kind of a construct, a theoretical construct to help with understanding diffraction, and it works quite well. So in this case, you have your incoming beam and you have a reflected beam. And so this is one lattice plane, and this one would be a second lattice plane, and the wave coming in here and reflecting off of there will have a little bit of a path length difference, and that's this green piece here. So you have to travel a little farther here and then a little farther here to get back into the perpendicular case. And then at long distance on the detector, these interfere with each other. And depending on what kind of path length difference you have, and here you have interference that can be shifted in phase slightly, and that can lead to reduction or reduction of amplitude. So the outgoing amplitude depends on the interference of different wavelengths at different lattice planes, and then in a crystalline lattice, you actually this path length difference needs to be a multiple, an integer multiple of the wavelengths, so to have constructive interference. And if it's not, then you have many of these planes and they're all shifted off a little bit, and the net result of this is that you get extinction for everything else. That's for a perfect crystal or for a large crystal. Now, if you have smaller crystals, if things get smaller, that destructive interference is not perfect, and you'll get some broadening. And from the broadening, you can then get crystallite sizes. You might be familiar with that as well. Small angle scattering is a lot similar to that, and that you're also getting size information, except we don't need a crystal lattice to begin with. But I'm going to go back to how we normally just get to the scattering vector Q on our side, how this is typically handled in scattering, in the scattering lecture. Scattering theory. So you describe your incoming neutrons or X-rays by a wave vector, which has a direction, and it has a wave number, which is just related to the wavelength. So lambda here is the wavelength, and that's just pi. And so you have an incoming vector, you scatter off of an atom or something, and you go into a different direction. You have this outcoming wave vector, and the difference, geometric difference of these two. That's Q, that's the scattering vector. So it is a vector, it has a direction, and it has a magnitude. And you can calculate the magnitude by geometric analysis of this little diagram, actually. And it turns out that the magnitude of this vector is given by 4 pi over lambda times sine theta half. So theta is that scattering angle that I defined earlier. Keep in mind that this theta scattering angle is actually twice the diffraction angle. So when you deal with diffraction, typically they talk about that theta, which is the reflection angle of the lattice planes, which is just half of this scattering angle. So this is the ingoing direction, and this is the reflected direction. So that's how the magnitude of Q comes out. Now, if you look at Bragg's equation, where you know that the distance is related to the path length and then to where your diffraction peaks are located, right? If you compare this term on this side and the one on that side, then you can see that Q and the inverse of the distance are very closely related. In fact, these two expressions on the right side differ only by a factor pi. So you can see that Q equals 2 pi over d. So for a Bragg case, if you have crystals, this is exactly true. If you have a non-crystalline system, there is still these interference processes still happen. They're just not as well defined as in the crystal lattice, but you still get interference, and from that interference you get information about length scales and distances in your system in a somewhat more diffuse way, but it's still this fundamental relationship of inverse Q and distance still holds. Okay, and then the magnitude is often expressed as inverse nanometers or inverse angstroms, so which you can see from this distance term here. Right. So I'm summarizing here something that's similar between scattering and diffraction and what's different. So I already said that diffraction requires crystals and scattering does not. It can be from anything else that's less ordered. The basic physics are the interaction of radiation with matter, and they are quite similar. There are differences in the instruments with respect to how we trade our flux versus intensity. So intensity versus resolution. So if you have diffraction, you often have very sharp features in your pattern on the detector, and you need a high resolution to resolve them well. So you don't want them spread out by the instrument itself. Whereas with the scattering and the small angle scattering, the features are much broader, and you do not need that high of a resolution, but your intensities can be low, and you're trying to push up the intensities by increasing intensity rather than resolution. But that's a bit of a side note, more of, that your instrument scientists need to worry about when they optimize your instruments. And of course, the data analysis is very different in most cases. You have very different systems you're working with, and data analysis between diffraction and small angle scattering is usually very different, although there are also cases where small angle scattering is the case of small angle diffraction, where you actually have large systems with crystalline order. So sometimes people have heard of colloidal crystals. We have colloidal particles that actually pack in a crystalline order, which then resembles that of an atomic lattice, but at much larger distances, then you get small angle diffraction, really. Right, so that's that. So one important feature is that when we have these very small Q, so when we're resolving relatively large structures, we are no longer sensitive to the atomic positions of individual atoms. We don't see them. They're not getting resolved in the measurement. Instead, we're seeing differences that are of somewhat larger distance. And then we can locally describe, rather than talking about atoms, we can talk about localized small volume elements that have an average scattering length density of the atoms that are in that volume element. And then you see the interference between these volume elements. So you're kind of, you're kind of going an order up in how detailed you look into the system. But the interference process still applies. So then we're no longer talking about the individual scattering lengths or powers of individual atoms, but rather about an average scattering length density in those volume elements. So we call this scattering length density, or SLD, and we often use the symbol rho, the Greek letter rho, which is also used for regular mass densities. The concepts are they are very similar in certain ways, but I'm not going to go into all of the physics of that. So we are then with small angle scattering sensitive to spatial in space non-uniformity of scattering length density. So we see variations of scattering length density in different parts of the sample. And so what matters in the end is not what the scattering length density in one volume element is, but rather how it compares to all of the volume elements around it. So what's the variation relative to other parts in the samples? That only gives you interference. If everything is homogeneously filled with the same scattering length density, then there's no net interference because everything cancels out, because you basically have wavelengths originating everywhere, and on average they then do not have any amplitude any net amplitude coming out, so it cancels all out. So local variations of scattering length density, that's contrast, and that gives you then rise to scattering effects that you can measure. And I'll get back to this later, but for now, I'm complete with this one. So then small angle neutron scattering intensity that we measure, like I said, it scatters off the individual nuclei, but then we average this to scattering length density, which is shown here as well. And the interference of the different wavelets from a distribution of scattering length density adds up as a net amplitude, and that's shown in this equation. So this is basically the central equation of all scattering and diffraction as well. So it's the interference, it's the Fourier transform, it's the interference of scattering from different parts in the sample, which are given by this radius vector, the position vector basically. And this expresses here the contrast. Again, the scattering length density somewhere in the volume element, in this case relative to a solvent. So that's what in the dilute case, this will be the solvent, is the surrounding. And the measured intensity is the magnitude square of that scattering amplitude. That's shown here as well. You'll often find it written like this. So this is a bit rearranged. So when we add this all up, there's a contrast term. There is also an intensity. So this is number of particles, and so this is for a dilute, usually for a dilute solution case. You can write it like this. So this is the concentration, so number of particles in the volume of the sample. Then you have a volume of the scattering particle, and that goes in squared. And then this P of Q is the Q or angle dependent term, the form factor we often call this. This is similar to the I of Q, but basically what we have done here is we have taken some constant terms to the front of it, and this P of Q then is normalized so that when you go to the smallest scattering angles to 0, as you approach 0, this will go to 1. And then this S of Q is a structure factor term. So this is the product here. I'm going to click the next button, so you don't have to remember all of this. So some important things here are this first term is a constant, right? We sometimes call that I naught or I zero or forward scattering. We have a form factor, this P of Q, which describes the shape of particles usually. And there's a structure factor that describes the interference between different particles. Now, if you're in a dilute solution, there's no net interference between the different particles, so this also becomes 1. Then you have a very simple case, and you often just see a form factor, and that's what you get in dilute solution scattering. And I'll be spending some time on what these form factors can look like in my next slides that are coming up. So, but this is some of the terminology that's used. There's another approach to getting at describing this, and that is to say that rather than doing the Fourier transform of the density and getting the amplitude and then squaring it, you can also go the other way around and use a scattering length density distribution and calculate pair correlation function from that in real space, and then do the Fourier transform. That also will give you the scattering intensity, and that leads then to the pair correlation function analysis of scattering, which I'm describing a little later in somewhat more detail as well. Okay, so I'll try to go through this a bit quick. You don't have to get all of the details that I'm talking about in the next few minutes, but I want to give this a little bit as a pedestrian approach, so to speak, to how you get bearings when you look at scattering patterns, and what happens if you change something about your particle. How is that reflected in the scattering pattern? I find that's somewhat intuitive when one has that kind of understanding. And if you're new to scattering, you don't know how to look at a scattering curve and what to make of it. So my reference point here will be a simple sphere of a certain size, which I will refer back to on several of these slides. So this is our sphere. I took a sphere with 100 angstrom radius, and this is what the scattering pattern of that would look like. Now, in this scattering intensity pattern, so this again is my 1D data, right, the reduced data. You can see this is a linear by linear representation of intensity versus Q, and you see this sharp drop off, and you do not see a whole lot of features here. Now, what we often do in small angle scattering is we use log-log plots, and then we can actually see some details that you might miss otherwise, and that's shown here. So it's the same curve, it's just a log-log plot of the exact same curve. So you see all these many oscillations. So if you have a simple shape like the sphere, you could actually, in theory, get all of these many oscillations. And sometimes when you have very good defined spheres, like some colloidal systems, you actually do get a lot of orders if you have really good data. More often, you lose a lot of these details. Keep in mind, this is a log scale. So if your intensity and your scattering signal is good somewhere here, the noise will catch you as you go farther out, and you will also have background. So one other thing to point out here, you sometimes get these envelopes. So if you imagine these intensities all smeared out into one, you would still get this kind of envelope slope here, which is a characteristic of another feature in scattering, and that's called Poirot scattering. And it's surface scattering. So it actually signifies that you have a flat surface. So our sphere has a flat surface. So if I zoom in, if I go to very small length scales, and remember that higher Q means smaller length scales, it's all inverse. You're not focusing on the sphere as a whole, but you're actually focusing on small surface areas. So you'll get the surface scattering at the higher Q as well. So that's that. Since I talk about surface scattering, this Q to the minus 4 decay is related to smooth, well-defined surfaces. If your surfaces have some roughness to them, like fractal roughness, this exponent will actually be a bit shallower. And there are also cases of diffuse interfaces where it can be steeper. That all exist. Now, once I add some background to my sphere, this is again the same sphere scattering. All I did is add some background. You'll see that a lot of the features again get lost, even though I'm in a log-log scale. But this constant background kind of overwhelms this. So once I put some noise on this kind of data, some oscillations due to noise, you lose a lot of this, right? So keep that in mind. So I've zoomed in now a little bit. This is our original curve that had this steep decay with these many oscillations, and this is what you might get in a good measurement if you have background. But this is again a high. This would be a very high quality measurement where you get these features. So what happens if I go from one sphere and use a bigger sphere? A couple things happen. Like I said, the features of larger objects will show up at smaller Q. So what happens here is these oscillations move from where they were before to lower Q. The bigger sphere has the oscillations tighter together and starting at lower Q. It's all inverse. So one other thing that happens is that the intensity goes up, and I have not normalized this new scattering going back to 1 to show this. If I would use the same amount of material in the system, but go from just let's say like if you measure your concentration mix per mil, if you keep these mix per mil the same, but if your spheres would aggregate into form a larger sphere, and in this case the diameter is twice as large, your volume would go up by 8 times, right? For a sphere, if you double the radius, your volume goes up 8-fold. Your scattering intensity would also go up 8-fold. So the intensity up here would go up as well. So just pointing this out so that you have another measurement here in the absolute intensities when you look at those in the end, that'll tell you what the overall mass or volume of your scattering particle is. In addition to, and that's independent, and is in addition to getting the radius parameter from where these oscillations are placed, for example. Okay, so now I'm going away from the sphere and make it a little bit elongated. So I have an aspect ratio of 1.5, so I'm a little longer in this direction than perpendicular. And this is what the corresponding scattering curve would look like. This is the black one. Here's again the sphere. You can see how these kind of move around a little bit. And they also get these minima get smeared out. So basically, if I have something that has more of a distribution of length scales in different directions, I'm actually smearing out some of these features. So this looks actually less sharp, the picture, than what you had before. What we typically will focus on when we analyze the data is, like I said, you normally won't get all of these oscillations, but what you will get is a difference here in this area here, where you can see that the red curve deviates from the black one. And that is actually enough information to distinguish ellipsoids from spheres in the scattering. And this is just an example where we have applied that. So these were very large so this is an electron microscopy envelope image from something called a chlorosome. And this was our fit that we used for the small angle scattering data that to overlay this, and worked quite well, this type of analysis. I'm assuming you can see my laser pointer, virtual laser pointer rather. Okay, so now I'm going to something called what I call a circular cylinder. This one has the same RG, so that's the RG is I'll explain to you in a second what RG is, radius of gyration. For scatterers, these two look very similar in that they have the same overall size parameter, this RG, but their shape is slightly different. So the RG is called radius of gyration. It's the root mean square average distance from the center of the scattering mass. So if you look at all of each volume element within the sphere and calculate what its distance from the center is, you get an average distance, and that's one of the most one of the parameters that you can measure with the highest precision in small angle scattering. Is kind of the first parameter you get out for everything if you have form factor scattering, that is. Now they look very similar, these two curves, otherwise, even though the shapes are different. So we're much more sensitive, for example, to changing this RG. If I made this sphere a little bit bigger, that I probably would see that better than if I use a different shape with the same RG. There is still a systematic difference, though. It's just hard to see. Now, if I put this on a different scale, I'm going back to the linear scale, just in the in the intensity axis. It looks like this. So you can see that there is a little bit of a difference between the red and the black curve, and that gives you information on the shape. So it's somewhat subtle, but in good cases with good data you can distinguish something like that as well. But if it gets noisier, so it might be hard. So what's the takeaway message here? If you have two particles that are in their shape distinct but have the same overall size, you might find it difficult to distinguish them. Now that is if they're both what I would call isometric. So in the sense, the cylinder that I'm showing here has a similar height to its width. So in that sense, it's more similar to a sphere. If I go now to something, I'm going to mention this briefly. There's something called Guinier analysis. What it does is it extracts the size parameter, this RG, and you can apply that to any shape object. So whether that's a sphere or a cylinder, it gives you this overall size parameter. So it relies on that. Like I said, we can measure this RG fairly precisely, quite precisely, even though shapes may be harder, may be different. There are also modified Guinier approximations to this. So this is coming from this exponential rollover here that apply to measuring thicknesses of extended objects and things like that. I'll get to this in a second. Okay, so you can do the Guinier analysis. I'm going to go over this a little bit more quickly. Yes, I want to catch up a little bit on time. So this is just focusing on the lowest Q, and you can get this linearization approach, and you get the overall size parameter, in this case for a sphere. So I said if I go to an anisometric object, so that is much longer in one direction than in the others. So again, this is a cylinder, but now you can see that this cylinder is much different from that sphere, and the scattering signatures are very different. They both still have the same overall volume and everything, but the fact that this one is so much more extended in one direction than into the other gives it a very distinct, very different shape. And in fact, this one-dimensional extension also shows up as an exponential decay that can be found here as the q to the -1. So this is, again, you can do the Guinier analysis also of this long thing. You can get this overall RG out, and the RG is similar to what we had before, but it's the same RG, right? So same overall size parameter when I look at all of the different distances from the center, but the shape is very different. So these two shapes I can distinguish very well, whereas the previous one, cylinder and sphere, I could not distinguish very easily because they were both isometric. So the cylinder was about as short as it was wide. So, okay, this is the last one of the shapes I wanted to mention. It's a random coil, so we find this for polymer coils. You find something somewhat similar if you have disordered proteins. They form these kind of very loose structures. The scattering curve is shown here in red. It has another significant or another distinctive power law behavior at the higher Q, which is a Q to the -2. And yeah, I wanted to show you that. So again, I used the same overall RG as for the sphere. This whole thing overall is more extended, so you have things farther out, but it's less densely populated. So these two objects again have the same overall size parameter, even though this one is overall wider, but it's just more distributed. And the scattering curves again are very different. This is the sphere, the black one, and this red one here is the coil. So you can certainly distinguish compact objects from diffuse random coil objects quite easily in scattering. Okay. I think I'm going a little longer than I thought. So this is the pair correlation function analysis I mentioned earlier. This is if you look at your if you're scattering objects from the overall idea of that I have distance distributions within that scattering particle, and then if I have different shapes, they will show up as different distinct pair correlations. So, for example, if I have an end-to-end dimer, something like this here, I will have scattering distances at short distances within one particle centered around here, and then I have another maximum here of distances that go from one particle to the other. So things like this will show up in the scattering. And the P of R analysis you can do directly by doing an inverse Fourier transform of your scattering curve, and then you can look at these pair distribution curves, and a lot of people find those more intuitive than the scattering curves themselves, because you can see from these peaks that something is happening in your particle. So if you have a bell-shaped curve like this, you'll have something very isometric. If you have something more extended, you'll have a tail and things like that. So that's somewhat intuitive. And then Wellington in his analysis breakout session, he will be talking a lot more about analysis of dilute solution scattering. But these are some of the common programs that I used, especially developed for protein scattering, although they can be applied to other things as well. So you can start modeling your scattering curves with different approaches, such as these speed models, where you start warm up in the initial and just move scattering blobs around until you get an optimized fit to your scattering curve. You can also sometimes use existing crystal structures and put them together in models if you have a multi-domain structure and rearrange them relative to each other so that you get the best fit of your scattering curve. So those are all different approaches of modeling your data. I'm going to go just briefly over this. I already mentioned the interparticle structure factor. This is basically when you have when you don't just see the scattering from one object, but from multiple that interfere with each other. If they have certain distances that are or arrangement that is preferred, then this will also show up as another term in the scattering function. This approach of a form factor times a structure factor works well in dilute solutions again, or somewhat more concentrated solutions. It depends though on that the form factor and the orientation of the form factor doesn't depend on the interaction. So there are some assumptions built in there. So this does not always work. It works for solution scattering typically, but one has to take this a little bit just with a cautious approach. I just wanted to mention this one briefly. You don't actually have to have well-defined distinct particles that you scatter from. You can have just a random inhomogeneity of your sample, and that's the case shown here, a very old one actually. Just this local variation of scattering length density from between different areas in your sample will give you scattering as well. And in this case, this is one case that appears, for example, in porous glasses and things like that. And then structural hierarchy of scattering. I think I might not get, yeah, I will get to that. So you can also have systems where you have a structural hierarchy where things build up from atomic to small to somewhat larger scales, and then you can have agglomerates, the aggregates, and that form larger agglomerates and things like that. So you can have multiple layers of organization of structure in your sample. And Venky's work breakout session tomorrow will cover this, how you approach modeling such data. So it gets, of course, a lot more complicated than just a simple form factor, but you still get information out. But it'll be in different types of parameters that will will not give you as much detail on the particle shape, but it will still give you important information on how these hierarchical systems work relative to each other. And our dilute acid pretreatment of switchgrass is such an example, and I think Wenki will be talking about this example as well. So in this case, we could see cellulose fibril diameters, and we could see how this we could see the cell wall surface at the lower Q. So we could see the different features in the sample at different length scales, and you can model this with hierarchical structure models, and they're actually fit curves of that model in these experimental curves. So, sorry, I think I'm going to be using up my time after all. So you already mentioned this one earlier. Scattering length density. We are sensitive to hydrogen in particular. Hydrogen and deuterium are very different, and because we are adding up the scattering lengths of individual atoms to calculate the scattering length density, that has another very beneficial side effect that we can actually, if you take water, for example, with 2 hydrogens and 1 oxygen, the 2 negative terms and the 1 positive of oxygen almost cancel each other out. And then if you make mixtures of H2O and D2O, you'll actually, for D2O, this large number, positive number, adds to the oxygen. That means that if you use mixtures of H2O and D2O, you can vary the overall scattering length density of that solvent over a large range, and that comes in very handy for highlighting different features in scattering particles by changing their relative contrast to the background. And I'll show you this movie just as this is another example of contrast variation, in this case using the refractive index of light. So you have the same beads in both of them, but you use a different solvent, and in water you see them really well, and if you use something, it's probably toluene or something like that, they almost disappear. So that's the kind of idea. You're changing just the scattering length density of your solvent, and you can make things appear or disappear. This is an example of a block copolymer micelle. This is a system that has 2 blocks of different polymer with 1 polymer block on the inside located in the micelle and the other one in the shell. And one of them was deuterated, and then we use mixtures of D2O and H2O, where you can adjust it such that you make the shell completely disappear. Then you see only the core scattering. That's this curve here. So that's basically a scattering curve from a smaller sphere. And then if you go to a contrast situation where we match the inner part, you'll see that shell scattering. That is this red curve, which it's a little bit lower Q, because this overall is a larger object than that one. And then something funny really happens if you match the average particle overall. So if I take the average from the inner and the outer part and match that to the solvent, then everything should disappear, and it does. Everything kind of does disappear in the forward scattering, where everything interferes constructively. But if you go to finite angles, you still get some construct. So you get some interference that still gives you a scattering peak that is related to the distance between the inner and the outer part. So one major takeaway here is that by changing contrast and not changing anything else in your system, you can get huge, very large changes in your scattering curves, and that's kind of a good thing, because that gives you then confidence when you have a model that you apply and you have different contrasts. That model needs to fit for all of the different contrast situations at the same time, which is given in this example here. So they actually fit curves of the model in these curves. They're a little hard to see, but they fit rather well for the different contrasts. And then we can also go a step further, and we can label our scattering object itself. So for example, proteins. So protein scattering normally matches at around 40% D2O in an H2O D2O mixture. You already mentioned that before. Now, if we deuterate the protein itself, so let's say we deuterate it by 50%, not completely, then my protein scattering would look like this, and it would match now at around 80% D2O. If I completely deuterate my protein, it'll go up to here, and that's not always useful because now I cannot match it anymore with H2O D2O mixtures. It'll always show up, and that's not always what we want. So often we aim for lower duration levels in small angle scattering than 100%. Okay, so this is basically my last slide. And so we have cases for neutron contrast. I may not read them all to you, but so there can be cases in your systems where you have zero natural contrast in electron density, for example. So this is a polymer mixture, a polymer blend, for example, just a polymer by itself. You cannot distinguish it from its neighboring molecules. If you label a few of them and put them in a blend, then you can see the individual calls and things like that. And sometimes it's just that you want to get more information out by using the contrast. Sometimes it's that we have just very low signal to noise. This is an example where we put protein in a silica sol gel, and you get lots of scattering from the gel and very little from the protein. But if you match the silica by H2O D2O mixtures, then you can still see the protein. So you can see a very low signal in what normally would be a large background by just making the background invisible, and then you find the needle in a haystack, so to speak, by making the hay invisible. And then often we specifically label in specific parts to highlight specific features in a very complicated system. And I have not talked about this at all, but there are lots of other neutron techniques, and especially there are also dynamic neutron techniques where you can actually look at the mobility or the motion of molecules or membranes or other objects of interest, and you can measure structural information at length scales at the same time as you measure motion or dynamics or vibrations or something like that. And that is also often very, very important or very helpful to have that both in the same measurement so you can pinpoint to where it's coming from. And I'm not going to read over this, but I think we will be sharing the slides. So it's a very large range of applications that you can have with small angle scattering, and it's often complementary. And the data analysis is very application dependent. I couldn't possibly go into all of the cases that you can have, but depends really on what you're applying it to. And so you want to work with your instrument scientists to if you're new to this, to figure out what's the right approach for you. And then I have some reference suggestions that you can look at in your leisure. And that's it. And I actually run a little over time, so sorry about that. But I think since we're late, I mean, I'm happy to take some questions now, but I leave it to Wellington how he wants to structure it. I'm also available at the break and then at the lunch break. So if you want to discuss some things more later, we can do that too.
Thank you so much, Volker. Yeah, I think we have time for some questions. We can take a couple questions. Thomas?
Hi. Thanks, Volker. Very, very interesting. I really love that talk. So I have a couple of questions. One about the anisotropic scattering. Can you use that in some way? So I'm imagining that if you had a contrast matched strain gel or a magnetic field aligning a molecule, you could control the orientation of the net alignment of molecules and somehow create angular components, kind of like in electron microscopy, where you do a tilt angle and a Fourier transform to get out information. Has anyone tried that with SANS?
Yes, and in fact you can. It's really the equivalent of diffraction, of more of the. So when you think about diffraction, there's powder diffraction and single crystal diffraction. These are kind of the extreme cases. But if you are able to put alignment into your sample, Hugh, I hear you in the background, I think. So sorry. So there is. So you will get anisotropic data. In fact, it has been done. Magnetic field alignment has been used for aligning membrane stacks, for example. So if you have like thylakoid membranes or something like that, and then you can make use of that. Yes. So the short answer is yes.
The neutron spin doesn't create a problem with using a magnetic field for alignment?
Oh, that's an interesting question. The neutron spin, and no. So now that would be if you have polarized scattering. So if you're sensitive to the polarization of, so you can also use polarized neutron beams, and then you could actually use that. But usually we use non-polarized neutrons, and then you're not sensitive to that. Yeah.
Last quick question. This is really fast. So how sensitive to imperfections in radius of a nanoparticle is the shell core analysis that you presented near slide 32 or something like that? I'm imagining that if you have widely different nanoparticle size, will that interfere with your ability to distinguish shell from core distribution?
I guess the short answer is yes, but basically, one of the things you see in the core shell system is, I'm still sharing, I guess. Am I sharing my screen still? Yes. Okay. No, too far. So one of the things that you will notice in a core shell structure is that in the shell structure you're getting, when you see the shell, you're getting more of an amplification of the secondary peak relative to just a simple sphere as this one. But if you have now a distribution of core shell particles, that basically would mean that you would have multiple of these curves that have their minima all in different positions. So you would spread all of this out. So you would smear all of this out. So if that depends on how much of a distribution you have. But basically, if you have a distribution of particles, they all add up. The intensity all adds up. So you get it all smeared out, broadened out. So it will interfere. How much? That depends on the case then. But you can basically introduce what we call polydispersity into a model like this if you have that kind of effect. Yeah.
All right. Shalika, do you have a question? Or hands
Yeah.
not on? Yeah.
Yes, I would like to know that if we have the cylinder shape and the sphere shape which have same RG, as you explain, we can't get the distinguished shape patterns of scattering patterns. So that means if we have that type of samples, this technique is failed, or do you have any other improvements, I mean, to distinguish those two shapes? And also, is it a rare situation?
So maybe I'll answer the last question first. This is a theoretical situation. I have not come across this one in practice. So I put these samples together because I was trying to take a theoretical approach where I can exactly calculate the scattering curves and see what it would look like. So I have not encountered this case. With regard to distinguishing them, so it would be, I'm not saying this would be entirely impossible to distinguish them, but you would have to have very high quality data. It would be very difficult though. You can distinguish a sphere and a cylinder very well if the cylinder is like extended, right? So this is an extreme case, but it wouldn't have to be this much extended. Even if it's a little extended, you'd be able to distinguish it from a sphere. Now, if they are exactly like this, the same, then that would be hard. So that was one part. So if you have a case like this, how could you improve on it other than measuring really high quality data? This would not be a great case to distinguish. Yeah, go ahead.
Volker, can I add one point?
Sure.
You had mentioned that in your talk. The main point is if the dimension of your cylinder's height and the radius are similar, that means that it is almost like radius in all direction of a sphere. That's when you get into this trouble.
Yeah.
You don't normally have that situation.
Yeah, that's right.
Okay, thank you.